PCA. You would use algorithms available in Python libraries to use application of PCA in a particular use case. So I'll be focusing entirely on the practicality of use of data. Feel free to interrupt me if you have any questions. I'm on full screen, so I may not be able to see the chat window, but you can ask me questions. So my agenda for today is to talk broadly about the life cycle of data, because we are talking about data collection and processing. But why do we care? We are statisticians. We are going to do statistics on the data. So why do I care about collecting and processing it? I can just use a laptop, get the data, and process it on a laptop. Why do I need to spend an entire hour on it? And the reason is simple. In large organizations, it's not just one person performing some statistical analysis. Used to be that way. Nowadays, you have team of data scientists. My background has been working for large companies, a lot of Fortune 25 companies in US. So the kind of experience I'll be sharing is how large companies operate. Uh, so in those large companies, there's not seldom one person who's doing any statistical analysis or anything, but it's a team. And it's very important that when you're working in a team, you're able to collaborate. You may not implement the entire statistical model by yourself, but you might be inheriting it from some other person who wrote it, from other team who implemented it, and now you will be asked to make it better. So students, when they do internship, it's a shock for them because they're just used to doing everything by themselves from scratch to end. And when they are in an environment where they have to read someone else's code to make enhancements to it, they're totally lost because they never had that exposure to be able to continue from where someone else left off. So I find students really struggling where they have to read someone else's code and make minor modifications to it. Similarly, nowadays, ChatGPT is there, students will take it, but if you ask them to edit it, they'll have no idea where to make the change. So we have to be mindful that we have the full overview of the big picture. That way, we can understand not only how to collect it, but how to collaborate it and share the data as well. So I'll be focusing on the collection and the processing part, but I will share two use cases, how exactly we used it in the company, what did we do, why did we do it, and so on, and some of the trends. And hopefully we'll have time for a Q&A as well. So when we talk about data, we just think, data is numbers just in an Excel or maybe data in a database, and that's all about data. No, the purpose of this slide is to show you there are so many aspects of data. So when we are processing the data, we have to consider all these aspects. So if I want to divide it broadly into three categories, one is the life cycle of the data. Your data originates in one place. So the use case we're going to talk about is a global manufacturing company. They manufacture sensors, and they have manufacturing plants all throughout the world: Philippines, uh, Africa, Asia, America, Europe, multiple plants as well. So they generate a lot of data, and there's always need to process and analyze that data, build predictive models as such. So when we talk about
Sir,
data,
sir,
yes,
sorry to interrupt you. Are you changing the slide because we are with only one slide will be appearing on the screen.
yeah, I'm looking at the enterprise information slide. It's a circle, blue and green color. Are you able to see that? Is everyone able to see it, or is it just for one person?
We are in use case slide, global sensor. I think it is the first one.
Okay, use case.
Sir, kindly keep the slide in the presentation mode.
Yes, let me stop sharing it. It is in the presentation mode, it's full screen.
Please share the whole screen. Probably you have
Yeah,
not shared the whole screen.
okay, let me do that. Maybe that might work better. Just a minute. Okay, I'm sharing my entire screen. This was the slide I was currently on. Are you able to see the slide now? And the slide
Yes, sir.
that was just the agenda, like what we're going to cover today.
Yes, sir. Now it is visible.
Okay, thanks for letting me know about it. So there are a lot of aspects of data. Data governance is important. As a statistician, why do I care? We do care because some of the practical challenges with data is not understanding what this data is about. You might get a spreadsheet and say, yeah, process it. Tell me, which of these parameters are correlated with each other. But if you don't understand what that data is and it just has some column ID and you have to interpret it, it's very easy to misinterpret what that data is. So when you're creating feature vectors and trying to understand that correlation, you could be misinterpreting the results. So the way to solve for that problem is having good data dictionary. A data dictionary is nothing but telling what each of those columns in the data means. What is the description of that data? But many times not many companies have it. So usually they'll have data governance, and the purpose of data governance is to basically make sure that everyone has good understanding of what that data is. So it's good data literacy. You know exactly what data you're looking at. So there's a data governance team that is responsible for managing the quality of the data, making sure that your data is well understood, the quality of the data is good, and we are cataloging the data. The reason we need to catalog the data is because many times you can get data from multiple sources, and it looks similar. So if we have like 6 manufacturing plants, I can get manufacturing data from 6 different places. But sometimes the equipment is not always the same. In fact, it is different equipment. So there are variations in the data, but the information is the same. So now I'm intentionally using the word information. So data is saying, I manufactured 100 sensors in the last hour. But the information and the data is saying, this manufacturer ID for this sensor ID, this was the timestamp and so on. But the information is, which sensor did I manufacture, and at what time? And that sensor ID is giving me the information about it. So data is very granular. Information is basically saying, what information is being represented by that data. So we go from data to information, and then from information we get insights. So information is basically saying, what did I manufacture? I manufactured sensors. Data is representing exactly the sensor ID. And insights would be, what did I manufacture yesterday versus, what would be my production today, and what would predicting my manufacturing capacity tomorrow. So we can have statistical models to predict that as well. So there is a lot of aspects of these data that need to be governed, and data governance team would do that. So in industry, if you're working with data, usually you will start and see where to get the data from, which data source I should be using for, and just making sure you've got a good starting point where you understand the data. Because if you don't understand it, then we can't implement a model. So that good data literacy is very important when practically implementing a project. Second aspect of it is the data architecture. So in the past, if it was a small company, they would have some sensors or some place where data is being generated, and they would process it locally. And the data architecture is simple. You have an equipment, you connect a cable to it, and now you are processing the data on your laptop. That was the old way to do it, not anymore, especially in large companies. You have the need for a data architecture because you're not processing the data locally. You're going to consolidate the data in a centralized location. So that way you get the big picture and you have an entire view of all the data. That way you can get better information. So in this example, we have 6 manufacturing plants. We don't want to store the data locally. It starts over there. The data will be generated locally in Asia. It will be generated in America and everything. But essentially, the data from all those countries, from all those manufacturing plants located in different countries, needs to be consolidated in one single place. So that way, Now we can ask insightful questions saying which manufacturing plant is the most efficient, or which sensor is produced in what quantities in which manufacturing plant. But if I have localized data, then I will just get information about one specific plant. So the key is to get the big picture and be a data-driven organization where we are taking decisions based on the data. Taking a decision not because every team is saying, we are the best manufacturing plant, we are very efficient, but the data is telling me how efficient they are. The numbers will say, this is what we manufactured, that's data. We manufactured 100. But my information is when I compare it with others, some others plant manufactured 300. Now my information is plant number 3 is manufacturing more than plant number 1. And my insight is, why is it that the other plant is not manufacturing? What are the causes for it? So there's lots that goes into data architecture. And the key part of it is moving the data where it is created. So if it's a manufacturing company, one of the key systems that they have is called manufacturing execution system. And I have a slide for it and I'll talk more about it. But data architecture is all about movement of the data, storage of the data. So that way you can process it at scale. Processing at scale means when you're consolidating the data, the size of the data becomes huge, because if it was one plant, it's limited. But now I'm aggregating the data, consolidating it at one place. So I need more processing power. I need more storage as well. And I need to have that capacity uh, that as data grows, my system would be able to still perform optimally. As more data has come in, I don't have to redesign and figure out, can I handle the data? And that's where the power of cloud comes in. So Azure Cloud, AWS Cloud, GCP Cloud, Google Cloud Platform. These are the three main cloud platforms. And most of these companies, they will use one or the other or multiple clouds as well. So data architecture is all about using those cloud platform services, bringing the data from the point of origination where that data is data is generated, and bringing it on the cloud. That's all data architecture is about. And where to store it on the cloud, in what format, that's what is decided by the data architecture team or a data architect. Once that data is consolidated and it's ready to be processed, we know it's good quality data, we have the data dictionary, we have the data catalog, then it is ready to be consumed by the data analytics team. And there are multiple use cases for data analytics. The old traditional use cases, traditional BI or business intelligence, which you can use with any reporting tool, such as Power BI or Tableau. Or small organizations who don't want to spend that much money, they will use Python and even visualize it that way without using a reporting tool. But for large organization, it is all about efficiency and being able to visualize the data so that data is telling a story. It's all about using predictive analytics. So there are different types of analytics. One of them is descriptive analytics, saying what happened. Predictive analytics is saying what will happen tomorrow. Prescriptive analytics will say, what should I do to achieve that outcome? Just like a doctor prescribes medicine and say, yes, I understand what happened yesterday. That's descriptive. You described it to me. I'll predict that, if I prescribe this medication to you, you'll feel better tomorrow. So we want to use data to know what happened in the past, and that's BI. That's typically done with reporting and business intelligence using a reporting tool. Uh, and then advanced analytics is more predictive and could be prescriptive in nature. And the way it is achieved is using AI machine learning models and then visualizing it. And since we have huge volumes of data, that comes under the realm of big data as well. And data warehousing is a key capability to process the data. So nowadays we have cloud data warehousing. Everything is done on the cloud. And these are cloud native data warehouses, which means you don't have to install any software on a machine on premise. Everything is on the cloud. So the key for data architecture is bring the data where it is originated, bring it on the cloud, and then use the computational elastic power of the cloud to process that big data, to implement machine learning models so you can do advanced analytics and you can predict what's going to happen. Okay. Any questions so far? Okay. With that, I'll move next. So the purpose of this slide is to show how the data originates. We produce the data and then we are consuming it. So realistically, if you're part of the data science team or if you're a data statistician, you are on the consumption side and you may be totally be agnostic. You may not have much visibility how the data got over there that you need to use. So the purpose of this slide is to show that there's a lot of pieces to it, which allow you to move the data, and then you might be just working in one team which is consuming the data. But it's essential to understand the full big picture from a capability perspective, how and where the data is produced, what are the key systems that produce the data, how do you move this data to the cloud, and what are the different choices and formats in which you can store the data, how you can then analyze and publish that data so that it's consumable by your data science team, your data statisticians, and so on. And underlying, there's some infrastructure to it. It could be on-prem, on cloud. Large companies by default it would be on cloud or a mixture of on-prem and cloud as well. But there are other aspects to it. We discussed in the previous slide: governance, which is saying governing, to have good quality data. The security of the data is important, and DevSecOps is to make sure that this movement it's put into production. Anytime when you build a model, you're not just going to build a model and say I use it. You're going to test the model. You in industries you have multiple environments. You have a dev environment, you have a test environment, and then you have a UAT environment, and then you have a prod environment. So if you are building a statistical model, uh, you won't just build it and say, okay, use it. It will go through that DevOps process, and a separate team will take your model that you've built and used it and tested it. They will test it on a larger data set and then deploy it into production. So DevSecOps will basically take your model and deploy it from dev environment to test into prod as well. So it's important to know that you're not the only one who's going to test that model. Other teams are going to consume that model to deploy it and build onto it and collaborate as well. So I'll start from the left side. What are the key systems that are generating the data as such? So if you are working in a company that has labs, processing, looking at materials, processing materials, and so on, realistically, you will have a software, an IT software system called as LIMS, which is for Laboratory Information Management System. IT is all about acronyms and systems. So realistically, companies, they won't just start building their own software. They will buy these software which are providing a capability to look at all the lab equipment, look at the quality for it, and process that data. And then that raw data is then given to the statistical team. But when it's given to the statistical team, it goes through this journey, and then the team would analyze that data. But the data originates over here. It could originate either in a LIMS platform, such as Star LIMS. That's an example of a software which provides that capability. But it's essentially uh, integrating with your devices, collecting all the data, consolidating it locally, and then could be publishing it on the cloud. Another key backend system is manufacturing execution system. Now is the trend for smart factories. What makes them smart is it is AI enabled. For it to be AI enabled and it to be smart, you have to collect a lot of data in each and every point of the process. So I'll jump one slide and come back to it. So what is MES? So you have a lot of data that is being generated in the plant. You're looking at all the sensor data, you're looking at the quality of it. There are a lot of aspects of it. Do I have sufficient material? Is the material meeting the specs, the quality specs for it? How many people do I have on the plant so I can schedule it to make sure they have enough to work on it as well? So all of these aspects of the manufacturing process is generating data, and is generating a lot of data for each plant, each equipment. So the key to be able to be smart about it is to be able to collect all this data, consolidate it, process it, and then derive that intelligence to say, yes, am I doing smart scheduling? If there is a shortage of a material, do I want to adjust the shift of my workers so they're not sitting idle because there's not this shortage of a material? That's happened during COVID when supply chain links were all disrupted. So you want to be able to adapt to those changing scenarios, and data and being able to use that, analyze that data using analytics model are the key to be able to make those data-driven decisions. So this is an example of what a manufacturing execution system does. The use case that we'll refer to used a specific software called Hydra X. Hydra is the name of the product that company uses to capture all these detailed data points to know about the manufacturing process, which is then brought into the cloud and then processed by the data science team. So a lot of systems are there. There is an ERP system. You have inventory. You have to manage the inventory. There's finance system. So some of the typical softwares are like SAP ERP. You'll have inventory management. You'll plan your resources. You'll have SAP Finance. So the key point is there are a lot of backend IT systems, a lot of data, and we want to move those data out of these systems and put it in a consolidated place. One of the other reasons why we need to extract data from these systems and not just do processing on the system itself is because this is all operational data. I know exactly how many sensors were manufactured today, but the LIMS software, the manufacturing execution system, doesn't care how many are manufactured 5 years back. Not relevant, because the operational manager at the plant just needs to know what was my productivity today. So these softwares, they will capture the data, but we don't want to store the data for long periods of time because it starts impacting the system performance. Because now I have too much data, and then the system starts slowing down. Just like on your laptop, if it gets old, it's getting old and slowing down, not because the hardware is slowing down, but it's just because you have too much data on it, and it has to search for a needle in the stack, and it takes more time. So to keep it optimally performing, we remove historical data and move it onto the cloud because it's not relevant. So I want to keep my performance to the optimal. So there is a need to move data from these backend systems and put it on the cloud. So the next question is, how do I move this data from these systems and put it on the cloud? So that is the data extraction or the data movement part of it. How do I move my data and put it on the cloud? So we talked about why do we need to move it on the cloud? Because cloud is highly elastic and scalable. We talked the need for moving it out of the system and putting it on the cloud to keep the system optimally performing. And the next question is, how do we move it? To move that data, there are multiple options, and it depends on organization to organization, which tools or which capability they use. Traditionally, everything was batch based, which means to move this data from MES onto the cloud, I would move it at the end of the day because the rationale was, why do I need to move it so fast? I'm going to do a statistical model on it, which I'm going to run maybe once a week, once a month. I'm not going to run on it every hour. So we'll just do it in a batch mode. That's how it was for many, many years. But now in the world of AI, time is of essence. So you want to minimize the latency or the time duration it takes from moving this data from here to the cloud. So you don't want to wait even a day. So if there's a problem with the sensor or you're manufacturing faulty paths uh, for those sensors, you don't want to wait for one day to realize that all one day worth of production was wasted because one of the sensors was not performing right, and the part was defective. So you want to be able to stream that data in near real time, maybe every 15 minutes, if not every 5 minutes, to be able to detect these anomalies in the data that we are collecting to know that one of the manufacturing plants is malfunctioning, and we need to look at it. So there's more and more appetite for processing this data in real time. So instead of using an ETL tool, ETL stands for extract, transform, load. There are different type of ETL tools like Informatica. Talend is an open source tool, and there are all these capabilities are there on the cloud. So if you're using Azure, there's Azure Data Factory, which will allow you to move the data. But there's more and more trend to do it real time, and there are different type of tools to do that. So one of the tool is called CDC, or Change Data Capture. And what change data capture does is, as and when you insert a record in a backend database, it will trigger saying these 3 records or these 10 records have changed, and it will create a JSON object for you and publish it. So now you can store it in the cloud, you can do whatever you want to do with it. You can process it in memory as well. But the key capability is that as and when changes happen in real time, you're able to broadcast and publish those data changes. So then you can have real-time AI models, you can process that data, whatever the use cases are. Nowadays, you have IoT streaming as well. So a lot of those IoT devices are generating data at the edge meaning it's outside your organization, outside the 4 walls of your organization. It's outside at, but now that device is at the edge of your perimeter as such. Now it's extending it beyond those 4 walls. So that's edge computing, but you don't have enough processing power to do it at the edge. You want to stream it and then process it. Similarly, when we get data, let's say from a satellite has minimal processing power. So we stream the data back to Earth, and then you can process the data because you've got a lot more computational capability to do it back where you consolidate the data. So that's why you want to stream a lot of this data. You want to publish it in Kafka or messaging as well. So that way you can store this data and consolidate it. In the past, it was easy. You just store your data on a file share. Not anymore, because the type of data previously was only relational. Now you have different types of data that you can process. You can process CCTV images to know, where there was theft or when the theft occurred, and AI can tell you based on computer vision algorithms that the theft occurred at this time in this image frame, and so on. So the type of data is no longer relational. It could be relational, like a comma separated value or a relational file in an Excel, save it as a CSV file. It could be semi-structured, like XML or JSON, or it could be unstructured, like video, audio as well. So the format of the data has changed. That has brought up all different types of different data storage capability as well. But the most common is the data lake capacity, the data lake storage, which is using what's called as object storage. So those who use cloud, there's something called as Azure Blob. On AWS, it's called S3. In GCP, it's called Bucket. It's always important to go from a capability perspective. Otherwise, you'll be lost if you're trying to use multiple clouds and you think, oh, there's too much. But the reason why I put this slide, and I specifically didn't put any names for any specific cloud, because this allows you to understand what are the capabilities. Object storage is a type of a storage which is very, very cheap. And that's why very popular. That's why when you're checking Gmail behind the scenes, Google is storing it in some NoSQL database or storing that data in some, archiving that data in object storage. So it is essential to understand these different storage formats. So what is the type of the data? Is it relational data? You can store relational data in a file, in a database. If it's XML, JSON, you can store it in a NoSQL database. You can still store data in a file share, but those are relatively expensive as compared to just storing it on object storage. But if you know what is object storage, then you know in Azure it's called Azure Blob, but it's the same thing. It's called GCP Bucket and GCP. But the capability, it's a very cheap form of storage, very durable. Data doesn't get corrupted, and you can store large volumes of data at a very cheap cost. And in industry, everything is very cost conscious. So object storage is the most prevalent way in which you can store the data. And once you have the data, you want to process it. So how do you process it? Again, there are multiple ways you can process it. But more important, what kind of processing do we need to do? Well, the kind of processing could be related with data quality. The other kind of data quality, meaning I should be expecting this data, but they're all null values. But I was expecting data over there. This data was mandatory, but there's no data in it. So I want to be able to enforce those data quality checks where that data was there, but I'm getting a null value. So I want to be able to know, create that data quality report and go back to the data governance team and say, I'm not getting good data. That's why my AI model is not going to work well, because I made the assumption that my data is going to always have this value. So that's called data profiling, where you profile the data, you look at any data quality issues, and then you can fix them as well. Many times you get massive amounts of data, but you need only 10 of those columns from the 100 columns that is generating. So I have to transform or filter the data. So I have a source data which has 100 columns. My destination, I need only 10 columns from that table. So in that case, I will transform the data, and data filtering is a simple example of data transformation. And I can process this in a data warehouse. I can process it in memory as well. So there are different software products which allow you to do that. You can use Databricks, which is Apache Spark. You can use data warehouse like Databricks SQL, or one of the most common data warehouses on the cloud is called Snowflake. And you can use Snowflake to process that data. So the kind of capability that a data warehouse provides. So a data warehouse is like a database on steroids. Database are meant for transactional. You're inserting data, continuously read write, continuously read write, but more focused on the write part. So if you have a backend database which is supporting a manufacturing execution system, then your that backend database, you're generating the data, so it's more write efficient. Whereas in the data warehouse, you're analyzing the data. You're not generating new data over here. The new data which you're generating is a result of processing that data which is already generated over here. So it needs to be more read efficient. Databases are more write efficient. Data warehouses, they need to be more read efficient. And you get that read efficiency by not reading the data row by row, but by reading it column by column. So that's called non-columnar data. That's why data warehouses are very fast. And the typical type of processing that you would do in a data warehouse is aggregation. So the example was which plant, manufacturing plant, is the best performing plant for given last quarter. Now, the data that I'm getting is, so the information I need is which is the best performing plant. The data I'm getting is, the data is not telling me which is the best performing plant. My data is saying the sensor ID was produced on this date at this time. And I'm continuously getting those rows of data, which will, if I aggregate it, I will know 100 sensors were manufactured in this 1 hour. If I aggregate it further, I'll get the information that 1,000 sensors were manufactured in a week. So if I keep aggregating it, if I keep summing it, I will know X amount of sensors were manufactured in 3 months as compared to Y amount of sensors were manufactured in 3 months. But I'm doing a lot of data computations. I'm doing a lot of those calculations at scale, at speed. Scale meaning the more the data comes in, I can still do it in that same time frame because I have that additional computational power because of the elasticity of the cloud. So you can process, aggregate huge amounts of data using a data warehouse software such as Snowflake as such. So that's what we process the data, cleansing the data, transforming the data. And then it is ready for the statistician to say, okay, this is all the data from all the manufacturing plants, and now I can use it. I can create my statistical data model in what's called as a notebook. So previously, you would write your program and, you would compile it in C and that's it. Not anymore. Because we are working in the cloud, it's collaboration. I want to be able to build a notebook. A notebook is nothing but it has the Python code which says read this file. And once it's reading it, I can actually see it has read the file. And I can pause over there before I want to do anything more with it. So it allows me to incrementally write code and be able to understand what am I doing with the data. So typically you would do that in a notebook. Jupyter Notebooks is a very common way of writing that code, and you can look at what that data is. You can profile it. You would use then this data for machine learning models. And we'll talk a little bit more about it later. But you can use it just simply to even visualize it. You want to see how many clusters are there. You want to use k-means cluster and see, what is my data? So you can visualize it. Or you can just simply create a report and saying which plant is performing best. Show me a bar chart or a pie chart, and you can do all those visualizations. You can have the data in a tabular format as well. So that's the consumption part. But to get to this consumption part, you have to move all this data onto the cloud, and then you can keep doing this even when you add more systems, add more data. This pipeline works. So this is a data pipeline, and it's scalable, highly scalable. That more data, no problem, it works. More people being added, no problem, it works, because you're not constrained by the capacity of one server where everyone is logging on. We use the power of the cloud. I'll take a pause over here because this slide is the key to understanding the rest of the slides. So I want to see if anyone has any questions or questions about why do we do it this way? Why not go directly from produce to consume? Why go through all this data architecture and consume this data? Any questions so far?
Sir, thanks for the insights. I have a question.
Sure.
Now that you're talking about the database, suppose a machine has to be controlled online. So, what is the strategy?
So to control that data online, you first need to be able to have that software which is abstracting and giving you a web-based interface to that machine. Uh, and that needs to be done securely. So most of these backend systems, they will have a web-based interface through which you can control it as well if need be. So LIMS has a web-based interface. Star LIMS has a web-based interface as well. So mostly, you wouldn't want to write that. So the strategy is using these softwares which have the capability, which have a web-based interface to control your equipment, but not only control it, but continuously monitor it as well. So you can do quality checks, QC on the equipment that is being manufactured or being used in the process. But that's the most common way, is using existing systems, software capabilities, which have that interface. You can certainly write your own, but then in that case, you have to understand what device drivers are there. So that way you can be able to build your own interface and have more flexibility with it. But it all depends, what drivers capabilities are provided by that manufacturing system. So Philips has a lot of devices they manufacture. They will provide you what's called as a device driver. Just like when you're installing a mouse on your laptop, it comes with a device driver. So similarly, these manufacturing machines, they come with these device drivers. You'll have to write the software which is using that driver and getting that data, and then remotely through web-based interface using HTTP protocol, you can control it. But it is quite complex and cumbersome. So realistically, no one would do that. They will just buy the software which will do that. And most of these manufacturing equipment companies, they will provide you a utility to do that. But you may have to extend it, add more to control it through the web. Did I answer your
Thank you.
question? Or
Yes, definitely. And you're talking about manufacturing systems. Let us say, can the design data like product lifecycle management and let us say PLM softwares such as Windchill, can it be integrated? Or let us say 3D printing softwares, can it be integrated?
Absolutely, yes. The answer is yes. How exactly to integrate? We have to first look at if that software manufacturer for that, let's say, 3D printing device, are they giving a utility through which you can integrate with it? So one of the most common ways to integrate is using API, application programming interface. So if you want to be able to communicate with any device over the internet, that device should support an API. So an API, the best way to understand and remember APIs, when you're using makemytrip.com, it is using API. It is using API provided by Air India. It is using APIs provided by Indigo, it's using API provided by other airlines. But an API is essentially a way in which you can exchange information over the internet in real time in a secure way. That's what an API is. So Make My Trip makes multiple API real-time calls to Air India, to Indigo, other airlines, and then you can see the comparison of the fares, and it's all happening in real time. Similarly, your machine would provide an API, and then with that API, you can integrate, and you can remotely control as well. Another example I can think of is in the biotech industry. There's a company called Illumina, and they build these machines called HiSec. And what it does is it takes a sample, could be a saliva sample, blood DNA, basically extracts the DNA and generates the genetic code, the DNA for it as well. So you feed in a saliva sample, what comes out of it is the genetic code. To access that genetic code, they provide an API. And these machines, they will actually automatically put it on the cloud, give you an API so you can retrieve it from the cloud using the API. So because these companies, they want to make it easier for you to consume the data and not focus your time and energy on how to get data out of the device. So they are making it more easier for you to be able to just use that API, or they'll provide you what's called as an SDK, software development kit, which will tell you how to use that driver. So you can write your .NET code or Java code to connect to that driver and do whatever you want to do with it. But APIs and device drivers, those are the common ways you would do it.
Okay. Can I have one or two more questions?
Sure, please.
With these automation and smart systems, the data is becoming crucial, as you said. Uh, is it the present systems ensuring accurate data compared to previous generations?
Yeah, so there are different aspects of quality of data. We call it as the 6 dimensions of data quality. So you talked about the accuracy of the data, but there are other dimensions to it. But to elaborate and answer your question, there are always accuracy related with the accuracy of the data. Many times, I'm giving the example of a manufacturing, but it always doesn't mean that it could be manufacturing data. A lot of these data comes from the web. A lot of companies, they will buy these data sources, especially your phone. It's capturing a lot of data, and these carriers, they actually sell this data because India just introduced a data privacy protection law. But prior to that, they would just bring this data and sell it. And the accuracy of the data was always questionable because that data went to one company, and one person can have 3 phone numbers, but for them, they don't know that. So they will say, yeah, this data is accurate and it's for 3 different people, but it's actually really not accurate because they don't have the KYC information, not legal for them to have it. So they will sell it as these 3 phone numbers are for 3 different person, but actually it happened to be for the same person. So in a way, it's not accurate. The data is complete. That phone number is valid. It is complete. It's not missing a digit. If it was missing a digit, I would say the completeness of the data is not there because it's missing a phone digit. That phone number is accurate, but it's not accurate in the sense that all of those 3 numbers are for 3 individuals. It's for the same person. So there are multiple dimensions of it. Is it timeliness? I'm selling a phone number which is 3 years old and it's no longer inactive. So it was active at some point, but now it's no longer active. So is my data timely? So that's why we want to make sure we move it real fast. We use CDC, use tools like Click Replicate. So your data is not stale. Your data is relevant because it's timely. But if your data is not timely, you're giving me data which is really old and it's obsolete, it's not relevant, then my data quality is poor because that data is not timely. It is unique. I could be selling a phone number list with 10 numbers in the list which are repetitive, the same number, because they want to inflate it. So is it unique? No. So my data quality is poor. So these are the quality checks you want to apply. But how do we know that which one is an issue? Is completeness an issue or is uniqueness an issue? And the way to do that is what we call as data profiling. You take the data, you say, okay, show me how many of these rows is null, how many of it is duplicates. So you will profile the data to then determine, is it actionable? Is this data actionable, or do I need to process it? Because if this data is null 80% of the time, then I need to filter it because this data field is of no use to me. Or I can go back to data governance and say, this data based on the description is really important, but I'm getting null 80% of the time. Can you please look into it and see what is wrong? Why am I getting only 20% but not 80%? Please look into it. So then we can address those issues. But if you don't know where the issues are, then it's a lot of fault finding. You're thinking there's a problem with your data model, but actually the underlying issue most of the time, it's actually the data. If you don't have good quality data, your performance of your ML model is not going to be good if your data is not good, if it has a lot of data quality issues. So those are some of the aspects of the data we have to look at, and some of it you can address it in a way. So if you have a lot of missing data, you can do what's called as data imputation. You can fill in that missing data by interpolation. So you can do that as well if it's relevant to the kind of data you're processing.
Yeah,
Did I
thank you.
answer your question?
And I have a last philosophical question. Yeah, I got the yeah. So now with the smart systems, the machine learning algorithms taking its position, what is the role? Because people are talking of AI. So what is the role of human beings or the engineers that you foresee in the future? Sir, I think, are you audible? For me, you are not audible, sir. What about
Hello, Mukesh. You're not audible.
I think is connection lost, sir?
I think so. I will give him a call. Just wait. Huh?
Okay.
Dr. Mukesh is reconnecting. There's some issue in the internet at his place.